Dan Beeker has over 40 years' experience in electronic system design and electromagnetic compatibility. As a principal engineer at NXP Semiconductors, Dan provides critical applications support for NXP automotive customers worldwide. He specializes in EMC and signal integrity design techniques for PCBs and systems, having completed over 200 PCB design evaluations for clients and internal NXP products. Since 2010, Dan has taught field-based design techniques at industry conferences around the world. His unique approach to EMC is a result of many years of collaboration with industry giants Ralph Morrison and Rick Hartley. Ladies and gentlemen, please welcome Dan Beeker.
I have a theme song. So.
It's all about the space now. It's all about the space now. It's all about the space, space.
All right, good morning, San Diego. How does it feel to be first? Isn't this amazing to be at the first Altium conference? I'm excited to be the first non-Altium speaker, so that's pretty exciting. I have some hard questions I want to ask first before we get started. How many people, have there any system engineers snuck into the room? This, just me and a couple more, okay. Usually when I speak, it's the opposite. I have 95% system engineers and just a few PCB designers. And so then I ask them, well, where's your design team? Why can't they be here? And the response is typically, well, they're busy working on an emergency respin of the boards we were working on, and we can't spare them. So that tells you how valuable the teams are. The other question I want to ask is talking about first. How many people have managed a board that went from first article to product certification with one spin of the circuit board? Look at this. These are the heroes. Yay. So that's the thing we want to talk about, is how important it is to do it first the right time. How many have done 4 or 5 spins in order to finally come to compliance? You know, depending on the marketplace, it can be easy or hard. I primarily support automotive, which is what I call high-performance, low-cost engineering, because they want to get the biggest, most powerful performance out of the product, and they want to spend pennies on it. So you're probably familiar with that mentality. The problem is that that doesn't lead to a lot of work up front where you really need to do all of the research in order to do the job properly. Billions of dollars are wasted every year by good-meaning teams designing products that are doomed to fail. And they're doomed to fail because the perspective is not correct. If you go after a problem and you don't have the right perspective on what you're doing, it's basically a matter of luck, rolling the dice, whether the outcome is going to be successful or not. So what I want to try to do today is to help reshape your thinking about what we do for a living. So we're going to talk about electromagnetic fields, that terrible, awful thing that even the double E's try to avoid as best they can. I became a digital systems engineer because I didn't want anything to do with that analog stuff. I could wire up with the best of them, and I knew how to do Boolean algebra, and I could even write some machine code. But that world has gone away, and what we're faced with are products that have converted every single design from what was a simple little controller like makes noise, a teddy bear that waves its arms, into a high-speed RF transmission system that you really have to know how to manage properly, or you're not going to ship your product. So the first thing I want you to start thinking about, and normally I play that song over and over and over again so that I brainwash everybody that's in the room, because I want you to wake up screaming in the middle of the night, it's all about the space. Because until that fact makes its impact into your thinking, it's going to be very difficult to start building the three-dimensional structures, printed circuit boards, that you use to provide management of electromagnetic fields. So the words are here. One of the key things is space is in there every place I could put it. And unfortunately, I had to listen to It's All About That Bass like 3 million times to get all the phrasing right. But the idea was to try to come up with something to make it easier to understand. The important fact here is the energy that we use doesn't move in wires. The wires have almost nothing to do with it other than to form boundaries for the field energy. And the field itself moves in the space between conductors. That's really a different perspective than what we were taught and what I ignored blatantly for the first 25 years of my career. So what's the things that have changed? We talked about change earlier, the movement of the industry. In the days when I first started working in electronics, the parts were in geometries that were huge compared to what we have today. The switching speeds were measured in milliseconds. We talked about things as a percentage of shrink in IDR rules. How big is this part? Well, it's a 65% shrink. Well, they're talking about the geometry, and we're going to talk a lot about geometry today. Geometry of the transistors themselves. And that's one of the most important guiding factors of all that we're going to do today. You need to know the geometry of the switches because that determines how fast they switch from off to on. And that is absolutely the most important thing you have to find from data sheets. Now that we're pushing into nano everything, if you hear nanoseconds, nanometers, you know that you have a part that's an RF transmitter. A nanosecond rise time is a gigahertz. And the nanosecond rise times are everywhere. Most parts are capable of many port pins that are switching in a nanosecond. We have new parts coming out that are going to be very attractive to your electrical engineers and especially to purchasing, where they have a part you probably paid $3 or $4 for in the past. It was in quarter micron or 180 nanometer geometry. They're moving it to this new part that's a 32-bit core with 4 megabytes of flash, and they sell it to you for 50 cents, and everybody's going, oh, yay. But these parts are in 32 or 28 nanometers. The transistors in this core are switching in 60 or 70 picoseconds. Now, all these numbers may not exactly make imprints on your brains yet, but I'm going to show you how important picoseconds suddenly are. The other thing that I want to say is that as we're giving you better transmitters, making it easier to make noise, the parts are also easier to disturb. So your customers are going to be even more helpful and extend the spectrum across which you have to be compliant, increase the amount of energy you have to withstand, and reduce the amount of energy you're allowed to radiate. Again, while I'm giving you something that's better at making noise and easier to mess up. So something's got to change. And what we're seeing across the industry is it's getting harder and harder to get the systems to pass electromagnetic certification. And that's because our perspectives are not correct. We're not taught right in school. The things we did successfully for years and years and years didn't work because they were correct. They worked because we were lucky. And that was, for me, that was the hardest thing in my career. I went to a PCB West meeting. Rick Hartley was speaking in a 2-day seminar. I was there because my PCB designer insisted I needed to go get some education because I was wrong about everything I tried to tell him to do. 5 minutes into Rick's class, I felt about this big. I knew that everything I'd ever done had worked by accident, not by design. And so then I spent the rest of that 2-day seminar making Rick crazy, asking him questions, because again, it was a group of of PC board designers, and I was the lone system engineer. And worse, I worked for one of the evil semiconductor companies. So you probably heard a lot of that kind of stuff. But there's no place to get the right sort of training. There are 2 universities I've found so far in the world. I have not been able to get anything added to that list yet. There are a few conferences here, because they're letting me talk about fields today. PCB West, the IEEE EMC Society has it, but the idea is that somehow the world has missed the connection between electromagnetic fields and their behaviors and what it really means to design some type of electronic control system. So we talk about simple things, volts and amperes, when it's really electric and magnetic fields. Volts and amperes are used because it's really easy to measure them and think about it. I can take my voltmeter, hook it up to a board, and see 5 volts, and that means something. I was told electrical pressure. Voltage is a measure of the electromagnetic field density per unit volume in the space that you're looking at. So you're not looking at voltage in the wires, you're measuring the density of field in the space between those 2 conductors. And amps are really coulombs per second. Coulomb is a measure of electromagnetic field. So when you talk about current from the generic perspective, it's how much field is moving past a space in a given time. It's a movement. It takes time. None of that's in the I equal E over R. There's nothing in the circuit theory that we typically apply that tells us what's really happening. What are the fields doing? What do I need to know in order to make the fields do what I want them to do? And what the heck are fields anyway? So that's what we're going to talk about today. Fields are what do everything. In the high-speed designs, everybody thinks about clock rates. Well, clock rates have nothing to do with the behavior of the field that you're trying to move from point A to point B. Don't tell me, a customer, well, I'm only using a 2 megahertz clock. So I don't care how often it hurts, I need to know how much it hurts. What is this switching speed? If it's switching at a nanosecond, it doesn't matter if it happens at once every hour, you have a gigahertz signal that you have to deal with. And every time that switch turns on and that energy has to move into that new space, you have to treat it as if it was a gigahertz signal, not something happening once a day. And that's the design parameter that we haven't been told about. So most important thing you have to find out from the data sheets is going to be how fast is this thing switching from 0 to 1. And if it's not on the data sheet, you need to start raising all sorts. You know, if you're a PC board designer, then make your systems engineers go dig this stuff up. Because you don't know what to do with the energy if you don't know how fast it's trying to move from 0 to 1. So first thing I have to put up is Maxwell's equations. Because if it wasn't for Maxwell being so smart, we wouldn't be here. So it's all about those equations and the ability of somebody who has such insight with, you know, there was no way to measure volts and amperes back then. This was all done from benign observation of phenomenon of electrostatic charges and all kinds of other crazy stuff. And these guys came up with this kind of information. But the equations talk about the interaction of magnetic and electric fields. There's no words about electrons or holes moving through that stuff, because I've heard it all, oh, it's holes moving through the wires, or it's electrons moving through the wires. There's nothing in Maxwell's equations, or in the real world that we live in, that has anything to do with electrons moving. In fact, one of Ralph Morrison's examples he likes to talk about, he said it's a 1/1,000,000th of the electrons in my body reacted within 1/1,000,000th of the electrons in your body, there's enough energy to throw the Earth out of orbit. So if we could actually tap into the electrons we thought we were using, there's all the energy to survive everything we'd ever want to use. But it's not the electrons. It's the electric and magnetic fields that make all the things happen. So the missing piece of the puzzle is that what we do for a living, we design and build products that create, manage, and consume electromagnetic field energy. Because all you can do is store it, move it, and turn it into kinetic energy. Fields aren't very much used for anything else like that. And when you turn on a switch, in the old thought, it means current flows in the loop instantaneously. So as soon as you turn on a switch, the load sees the energy. If that were true, then we wouldn't have problems with signal integrity or EMC. They would happen by default. But what happens when you turn on a switch is that you've just added a new space next to one that has field in it. So when the switch opens up, the field has to move from behind the switch into the new space. And this takes time. And it has all kinds of crazy things that happens. It doesn't like instantly start flowing. You have a bubble of energy that starts to move into this new space, and it goes down until it finds something to reflect off of. It causes a negative bubble, so we have a sourcing wave going one way, a depletion wave going the other way, because it's pulling the energy real close to the switch into this space. And then that starts another wave that goes back and looks for more field so it can bring it back and fill this space until both spaces have the same amount of charge per unit volume. It's really straightforward the way it behaves. And there's no magic here at all. Current flow, we talk about current flow. Like I said, an ampere is a coulomb per second. So it's a measure of how much field is moving through a space. Resistance is really a feature of a conductor that tells you how much it's going to interfere with the movement of that field. Because as the field moves through these spaces, unless it's outer space, the fields have to mess with every molecule it comes in contact with. So in the conductors, the fields are banging around trying to move the electrons that are in the conductor. That causes them to vibrate. It takes some matter amount of the electromagnetic field is converted into kinetic energy, heats up the wires. Voltage drop is how much of the field did we lose as the field was playing with its friends in the molecule world. You also have the same thing happening in the dielectric. As the field moves through the dielectric, there's molecules in there, not as many per cubic centimeter as in the metal itself, but there's still a certain amount of the energy is being converted into kinetic as the field moves through this space. That's why things heat up. It isn't something magic. It's because the fields are making the molecules crazy. So fields are moving through. You've got conductors on each side. The field has to say hello to everything. And during this magic event, while the field is moving through these spaces, only a very few microns, of the metal are actually involved in the movement of the field. Not the whole piece of metal. And we were like, oh, but the current's through the whole metal. No, it's not. It's called skin effect. You've probably heard that, but not really understood it. It means that the crystal lattice is so tight in the metal that the field can only mess with a few layers of them before it's moving on. So it doesn't have a lot there. Even in high voltage transmission lines, in order to get the distance between the big towers, they use a core of steel and a few microns or a few mils of copper on the outside. because even at those potentials at low frequency, it's still only a few mils of the metal that are actually involved in the movement of the field energy. So it's all about the surface of the conductors giving a boundary for the field to live in that space. And then it takes time. It doesn't mean jump over to there. It has to make its way over there. It's some terrible thing called the speed of light, or depending on the dielectric, something less than the speed of light. Because by the time it says hello to the molecules in the dielectric, it slows it down effectively. That's why you have dielectric constants. A decay of 4 means it moves at 1/4 the speed of light, because it has to say hello to everybody. So wasn't taught that. It was taught about, electrons and wires and hooking things up, and why does this have to be so hard? But it's not. The reason we have been able to get along for so long is because of the technology of the devices we were using. But we've got to change things because the materials we use have changed, and the rules that we have to play in as far as the compliance requirements have changed. So we talk about fields. Until Ralph Morrison got hold of me and Rick Hartley, fields were, to me, nothing I cared about. If fields are invisible, they do what you tell them to do, they follow the traces, they're somebody else's problem, only for farmers. And I was, like I said, I'm a digital engineer. I don't want nothing to do with that RF stuff. I had friends who were RF engineers, and I treated them well because I knew they were smarter than me. So we talk about fields. Fields are contained in a space because that's where they live. Okay, so if I've got a sphere and there's a conductor inside that sphere and there's some field stored in that space, it will be, I don't know how good this is going to work, not. It will be in the space between the outer surface of the inner conductor and the inner surface of the outer conductor. And unless there's a hole in that sphere, the field cannot magically escape through the metal. For field to be present, you need 3 things. 2 conductors separated by a space. 3 things. If one of those conductors is continuous, then you can't take the field from inside of the continuous metal and be outside. You need a space. So the only way you could do that is if you have a hole in the sphere. So if I've got a sphere with a hole in it, and there's a conductor in the middle, and there's field in that space, and there's another conductor someplace in the universe, there will be field energy between the outer surface of the inside conductor and the outer surface of the conductor that's outside of the sphere. And between that conductor and ground, and that conductor and the wires in the wall, that conductor and planes flying overhead, that conductor and satellites in orbit, and that conductor and Betelgeuse. Because the law that Maxwell has figured out is between any and every pair of conductors, there will be shared field energy. And the only reason things work at all is because the magnitude of that energy is reduced by the square of the distance. Because the farther things get apart, the more field it takes to achieve that balance, the field density that I'm looking for. So farther apart, with the same potential or the same amount of field, it spreads out. It's like if you have a propane tank that's full, it weighs 7 pounds, and a propane tank that's half full, weighs 3.5 pounds. They look the same, but the amount of field or gas per cubic centimeter is less. The same thing with fields. When they're in a space that's larger, the field, and you have the same amount, same number of coulombs of field, then it gets dispersed. Therefore, you have this ability to withstand the fact that every field, every signal is spread out between every single conductor on your board. In a circuit board, you have thousands and thousands of pairs of conductors, and every signal is going to be present to some extent in every one of those pairs. The good news is the magnitude of the distance, right? So if I have two signals over traces over a plane rather, most of the field is going to be between the bottom surface of the trace and the top surface of the plane. Now there will be field between the two traces by law. Maxwell says between any pair of conductors there will be shared field energy. If I have a trace underneath that, there's no way for the field that's on the top of that copper to make its way to the bottom of that copper through that metal. Doesn't happen. So if I have clocks on the top, I can put a sensitive analog signal on the bottom without having to worry about it being contaminated by dirty ground. Because ground can't be noisy or dirty. Ground is one conductor. A conductor has nothing to do by itself with field movement or energy. There will, however, be some energy that's going to sneak around the edge of the PC board and come back over here and find its way to your sensitive analog trace. But again, the square of the distance rule comes into play. You have about 200 dB of separation. So for most anything you ever are going to work on, you can ignore that type of interaction. But the only way the field energy is going to go through that board from the top of the copper to the bottom is if you put a hole and another conductor. You have to always obey the law. You have to have 3 elements for field. 2 conductors separated by a dielectric. So to keep control of fields, you have to know the space that you have them in, where you're storing them, how you're moving it, and where you want to consume it. So now we're going to talk a little bit more about some physics here for a minute, but I'm going to try to keep it in a level that it's easy to understand, because I don't understand the math. I understand pictures. Everybody talked about antennas. When I went to these classes, and I've been going to PMC classes and PCB design classes for more than 10 years. I've probably seen Rick Hartley speak about 20 times. And I had to keep going back and over again. After about 6 years of this, my boss said, well, when are you going to start teaching this stuff? I'm paying for you to go to these classes. I'm like, oh, I don't know what to do about this. I'm like, I got to learn more. So I got an email one day that said, we're going to have a conference in Brazil, and you're going to teach a PC board design class. And I went, I don't have a PC board design class, but I'm going to Brazil. So I said, okay, I'm going to go. Somebody's paying me to go to Rio. Oh, yes. And so I'm like, what do I do? How do I make a class that makes sense? Because I don't know if you've probably been to lots of PC board design classes, and a lot of it is just really hard to absorb. You know, sometimes they talk a lot of math and talk about a lot of other things, but I kept hearing things, and some of them made sense, and then this guy says this, and this guy says something completely different, and I'm like, who's right, and how does this work? So I started, how do I pick out the stuff that's important? Because I got to go teach my customers how to make their boards right so they don't make me crazy as I have to help them redesign them. So the big thing they always talk about is antenna length. So quarter wavelength, that sounds exciting. So I started, okay, let's start with antennas. Antennas are important because if you don't have an antenna, you can't radiate or you receive. So you can't interfere, nor can you be interfered with if you don't have the right antenna. So that's a good place to start. When you look at it from the analog perspective, at 90 degrees in a cycle, when you go from 180 degree or 360 degree cycle, at 90 degrees, the voltage or field density is at its maximum, and it's changing the least. So current is at 0, voltage is maximum. So if you present at that length of an antenna, that's a quarter wavelength of the switching device, then most of the energy is here, and if the conductors suddenly stop, it's going to tend to keep going. So at that point, you're presenting as much energy to the outside world as possible. Same thing going back in. You have a better way of bringing energy in. So this kind of made things go off. So I built this chart, and actually I started at 0 and went to blue light. And this is where everything started to finally make sense. When I moved to Detroit in '87, it was when the semiconductor vendors had gladly moved everybody from HMOS to HCMOS. You know, our new parts are cheaper, faster, better, and every module failed EMC. And that's what I walked into. And I had worked on radar one time, so I became the EMC guy because I could spell EMC. And so I spent many, many days with customers sitting by chambers and trying to figure out stuff, and it was a nightmare. When I made this chart, I could tell what happened, because before I had no clue. At HMOS, if you're not working on a train, a bus, or a tractor trailer, there's nothing long enough in your system to be a radiating antenna. When we went to HCMOS, it switches 10 times faster, which it's all ratiometric, which is what I love about this stuff. The geometries are really simple. It's algebra. I can do algebra. It went from across the room to about this long. And every module in automotive has a wiring harness at least this long. So we gave them a radio transmitter, and they hooked it up to an antenna, and they had their own broadcast station. And it was like, oh my gosh, now I know why it all failed. I wish I'd have known this 20 years ago. I wouldn't be here. I'd be rich, like some of these other ENC guys. As we moved through the food chain, though, at a nanosecond switching, radiating antenna is about this long. So now your circuit board is covered with hundreds of potential antennas, both for radiating and being disturbed. As we move deeper into the shrink, the 65 nanometer stuff, you're looking at wire bond and lead frame are long enough to be radiating antennas. At the new stuff we're working on now, 32, 28, 14 nanometers, metal on the die can present a length long enough to be a radiating antenna. Traces in the substrate or interposer are long enough to be half-wave antennas or longer. You have these wonderful radio stations. We're putting them in antenna farms like a quad flat pack, and you are supposed to build a product that's compliant without throwing a whole bunch of covers over it and wrapping it in foil like my customer had to do with one of their displays. This is why things changed. We had things working because we were somewhere with our methodologies about TTL-ish. HCMOS each. We were doing things that got us through those generations of semiconductors. But we're way past that now. And either we have to change our philosophy, or we're going to continue to do 4, 5, and 6 spins on a board, each time praying that it's going to work when it comes back. If you have the right perspective and this field-driven philosophy, when you make a board, you're almost completely confident that you're going to pass CMC, because you've designed the three-dimensional structures that match the energy that you're trying to control. So we got away with everything because the switches were so slow, and the relative conductors we hooked them to were so small. But since the days of TTL till today, we've gone through 4 order magnitude change in switching speeds. 4 orders of magnitude. Let's talk about what that means. 0 order is the buggy that goes 6 miles an hour. The first order increase is 60 miles an hour. And the only way that buggy's going 60 is if you throw it off a cliff or stick it on the back of a truck. Completely different solution. 2 orders is 600 miles an hour. You're in a jet airplane. Completely different solution. 3 orders, it's 6,000 miles an hour. We're in a rocket ship at this point. A new solution to the problem. At 4 orders, it's 60,000 miles an hour. You're in an alien spaceship. So only in the electronics industry will we try to go through a 4-order change in the behavior of the energy that we use without changing what we teach or what we do. And the results are consistent failures. Not because people don't want them to work every time. I mean, everybody wants your product to work, because that's where you get to be the hero. But if you don't have the right philosophy and change the methods, you're stuck with trying to make the buggy go 60,000 miles an hour. So what we're going to focus on now is called a transmission line. The generic view is conductor, dielectric, conductor. And a lot of people hear the word transmission line, they instantly go to controlled impedance. That's a special kind of transmission line. And sometimes you need that. But where you want the energy to move, where the energy will move, whether you care to its that's right or not, is in the space between two conductors in a transmission line. Now, the reason the energy goes into this space, as we talked about a little bit before, is to get the same field density per unit volume. It takes less field in a smaller space to give you 5 volts than it does to fill a space that's larger. The impedance of free space, which is basically two conductors at an opposition like this, is 377 ohms. So as you collapse that space, the amount of field it takes to put a given field density in is reduced just because the volume is reduced. So this is about three-dimensional spaces and the volume that they represent, or how much field does it take to fill that space. So every conductor pair is a transmission line. What we have to do is make sure that the transmission lines that the energy flows through are the ones we want it to. And it's actually a pretty simple thing. One of the conductors needs to be continuous from the source of the energy to the final resting place, whether you send it to, whether you consume it into a motor, whatever it is. One conductor is continuous. That's system ground. One of the things most EMC guys like to say is if they see more than one symbol for ground on a schematic, they know they're going to make some money. And I don't care if it's your data sheets from your favorite semiconductor vendor or application notes, if there's more than one ground symbol on there, they don't know what the hell they're talking about, and they're setting you up for failure. Because it's almost impossible to manage discrete domains for the energy. That says, if I go to analog ground 1, and I need to make that energy, everything that makes that transition has to stay in that range. It can't lose its context. There are some places for that, but 99.99% of the time, it's not going to do anything but make your system noisy, reduce the signal integrity, and cause EMC. So when somebody tells you to put a ferrite in ground, or an inductor in ground, or to separate by a little neck of copper, and then route a whole bunch of signals into that, especially the A to D converter guys, they want you to do that. They have no clue what they're talking about. Dr. Todd Hubing will repeatedly say, and I repeatedly say, is thou shalt not split ground. So that makes it, first thing is easy. We know what one of the conductors is. It has to be unbroken from where I get the energy to where I'm going to use it. The second thing is easy too, the dielectric. I have to have a constant, unbroken dielectric next to this conductor from this place where the energy comes from to the place where I'm going to use the energy. So the only thing I have to worry about designing now is the conductor that I switch that allows me to take energy from this point to this point on demand. Some of those switches are pretty fancy. Voltage regulators, they're a variable switch. Some of them are super fancy. A microprocessor is just a multi-port power distribution system. Lots of switches that turn on and off and let you take field from here and put it there. Is this starting to be simpler now? Easier to understand? It's really easy to manage fields. This is my new rule of triplets. You get three components to use. You get a conductor, get a dielectric, and you get a switch. There isn't anything else that you're using. There's components that have millions of switches, but they're still just switches. They turn on and off. They allow field to go past them through the space they're guarding, or they turn off the space by disconnecting one of the conductors. Really straightforward. And field, it's pretty useless. They only do 3 things. You can store field, you can move the field, or you can convert it into kinetic energy. There's nothing else you can do with field. It makes things vibrate, heats them up, makes lights, makes motors turn, makes speakers vibrate. That's pretty much it. All you do is take field from here, take it to there. Hopefully you've not lost so much of it in the movement as it interacts with your conductors and your dielectric that you don't have enough energy to do what your job is. But that's all there is happening. You're just moving field. So basically we're all plumbers. with really leaky water pipes. Because the doggone PC vendors, they won't build coaxial interconnections, so I don't have to worry about fields interacting with each other. So we just build three-dimensional structures that allow us to control field coming onto the board, being redistributed and doing things, communicating information, doing logic functions, and then causing something exciting to happen like turning a light on or turning a motor on or whatever it is our product is supposed to do. But designing those three-dimensional structures is where good PC board designers can flourish. We've got some extraordinarily powerful tools. We have to make sure that we tell the tools the right things to do. That means as we move signals from off the board, through the power supply, into the ICs, that we give that an unbroken path with only one conductor being switched. We take that energy and we do stuff with it, distribute it to the board, do logic interactions, do kind of things, and then move it around, and finally at some point we do some kind of mechanical function. But we're building three-dimensional structures, and that's not just in the X and Y axis, it means in the Z axis. When you go through the board stack, you have to make sure that the rules are still followed. It has to be a continuous conductor, a continuous dielectric, and then whatever it is your switched conductor is. Whether it be signal A, address 12, power supply 16, it doesn't matter. You only get to play with one of them. And that's where we fall apart. We don't make sure that the signal trace, the power supply trace, is always one dielectric away from the return, system ground. And that's where signal integrity falls apart. EMC becomes something difficult to achieve because you don't have a place for all the fields to live. If you don't have one dielectric between each signal and ground, then you have multiple signals that are living in the same space, and they don't leave each other alone. They mess with each other. So if this one's 3 volts and this is 2 volts and they get together, you've got 2.5 volts. Well, that isn't what you wanted. So the idea is to be able to get the energy from where I'm switching it to where I need it to be without having it corrupted to the point where it has no value. Either has to present a digital pulse train or provide an analog voltage. We have to get it there without it getting so messed up that it's worthless or that it causes its neighbors to be worthless. So with these two conductors and a dielectric, we can build some cool things. One is a capacitor. Capacitor is 2 conductors separated by a dielectric that's used to store field energy. We connect one side of each of the conductors to the circuit board. The other side's open. And it takes a finite amount of time for energy to be put into this capacitor and a finite amount of time for the energy to be removed from the capacitor. It's all about time. An inductor is not some magical thing that resists changes in voltage or current. An inductor is a way of increasing the space between the ground and the switched conductor. Because you put a big old component up there with lots of windings, it's got a volume of space that's significantly larger than a trace over a plane. It takes a long time to fill that space compared to what it would take to fill the space between the traces. So when I stop, so it stores energy effectively in series with the transmission line. So when I turn off the switch that's helping energy move into this space, there's still field energy in that space. So now it has to be redistributed. So then you'll see the field coming out of the space that's defined by the inductor and the ground to go both directions until equilibrium again is established. So the field density throughout the entire space is the same. But all this stuff takes time. But it's not magic. It's a great thing when you're doing a switching power supply. You turn on the switch, you fill this space with energy, turn off the switch, and then this energy is directed into a capacitor or a diode or something. It's a good way to take small chunks of energy and create a smaller density. In the case of a normal converter, or in the case of an up converter, it'll store it into another structure to give you a higher density through a diode. That's good for doing that. But the idea of putting an inductor in series with a power source is crazy. Why would you want to slow down the movement energy from where it is into your switch array and then redistribute it? Not the less put one on both power and ground. So the idea is to move things sufficiently and use them where they're appropriate. So signal traces, power traces, it's the one dielectric rule. You really have to make sure you never break that rule. And then the only thing is that as long as the driver and receiver are a certain distance apart, you don't even care about the impedance or the volume of that space. In fact, my goal is to have no requirement for controlled impedance, and I design the lowest impedance that I can afford so that it takes the least amount of energy to fill that space. It reduces overall power consumption on the system. But if you've got drivers that are farther apart from the receiver than a sixth of the wavelength, then you have to worry about matching impedances and preventing something called ringing, and we'll talk a little bit about that. So when I take a low impedance driver and I drive energy into a transmission line and there's the same impedance, I get perfect match and the energy goes through here. If I have a low impedance and I drive into a high impedance, I get a reflection at the receiver at twice the amount of energy. So if I send a 5 volts down there, it bounces off and comes back as 10 volts. Goes back to the other side, hits the low impedance, it gets a negative reflection, and it goes back and forth until that field energy finally radiates or is converted into kinetic energy, heat. So it looks like this. If I've got a wave, if I switch fast enough that I achieve full voltage level before the wave has found the receiver, I'm going to get all the energy reflected back. Hits the low impedance, it comes back as a negative, and that energy just starts sloshing back and forth and back and forth. So the idea is this. If I have a little hole in the wall and a bucket of water, and I throw it at the hole, some of the water is going to go through the hole. But most of it's going to splash back on me. That's low impedance to high impedance. And that's what you see in your systems when you have ringing. Low impedance or high impedance to a low impedance is I take the bucket and I throw it out the window. All of the water goes out. My bucket's empty, and it doesn't reflect back as an increase in field energy. It comes back as a decrease in field energy, and it is a depletion wave that moves back the other way. So most of the places we do things are within a sixth of wavelength, but what we have to do is think about the idea of making things lumped and when we don't have to. So in this perspective, we have to think about things in a digital realm, which is 0 to 1 and 0, because you don't do any negatives in a digital world. So it's not a 90 degree anymore, it's 180. So it looks like this. So I go to maximum voltage is at the half wave or 180 degrees. So a sixth wavelength for me is a conservative goal for lump distance. That way I never generate more than 2/3 of the incident voltage. So if my design team can't put it exactly a sixth wavelength, they can put it a little farther away, I'm not going to care. I'm still going to have low reflections and never have the second order reflection that goes over to all the way to the driver. This is again the reason things worked in the past. In HMOS days, if it's in the same room, it's lumped. You never had second order reflections. Even with HCMOS, if it's on the same circuit board, you're okay. I wire wrapped a 68020 single board computer on a VersaBus board. And it worked just fine. I thought it was because I was really good at wire wrapping. It's because everything was lumped. I just didn't know. When you get down to a nanosecond, you got about 2 inches. If you're driving a nanosecond, you better have the receiver within 2 inches or you're going to have to do controlled impedance, which means putting a matching impedance device, a series resistor, inside the lump distance and then route a controlled impedance 50 ohm line to the receiver. As you get farther and farther, you can see why DDR3 and 4 have on-die termination, because by the time you get through the wire bond, you've already way beyond the lump distance. So power is the other side of it. So I'm turn on a switch and energy is going this way. Well, how do I manage the sourcing of energy? Because what happens when you turn on a switch, you get, if it's a nanosecond switch, I get a nanosecond edge moving into this space, sourcing energy. Well, this causes a nanosecond edge of depletion wave that's sucking energy out of here that goes back the other way. 90% of the EMC issues that I look at are caused by not the output driver, which is what we were always told, it's the outputs that make it. It's by the depletion wave not getting energy fast enough. So the noise comes from a poor power supply, not from a fast switching device. And the way you fix it is to improve the power distribution system. In most cases, I can almost guarantee they have broken the one dielectric rule somewhere between the power supply and the IC that needs the energy. So it's two ways. So if I need energy from over here, I got to go over here with my depletion wave, grab the energy and bring it back and throw it into this thing. And it goes back and forth. So you have to go back and forth to get the energy. So when we talk about how long does it take? Well, if I've got a 50 ohm line, a typical transmission line on a board, and I need an amp, and I've got a 5 ohm load and a 5 volt source, I can get 1/10 of an amp, which 1/10 of a coulomb per second, through that space. If the space is only a 1/16 of an inch long, it takes 10 picoseconds. So like I say, I can't get it all at once, so I got to go and get it. So even one round trip through a 1/16 of an inch is 20 picoseconds. Well, if I need a full amp, a coulomb of energy, it's going to take me 10 coulombs, or 10 of these round trips minimum. But it don't always get the same thing. So what I end up doing is it takes 30 full round trips to move an amp of a coulomb of energy through a 1/16 of an inch. So it looks like this. It's a series of steps. The height of the step is the impedance of the transmission line. How big is the bucket? The length of the step is the round time trip it takes to go there and come back. So step 1 is X, step 2 is 2X, step 3 is something less, and finally you get to the top and you build the charge. This is exactly how capacitors work. They're not a magic curve. It's a series of steps determined by the length of the conductors inside the capacitor and the impedance or the capacity of that dielectric. Unfortunately, capacitors, their dielectric constants are huge, 10, 20, 30,000. So the energy moves really slow through those spaces. So that explains a lot of the things about how capacitors go. But the problem is everything's a 1/16 of an inch. You know, connections through a pipe. You know, a lead frame and wire bond is a 1/16 of an inch. Connections to capacitors. So now, back to picoseconds are important to you now. Because picosecond, 10 picoseconds now is a 1/16 of an inch. That's something you're going to need every day from now on. So for power sources, it just took the same equations and put them in. So if you have a capacitor within 4 or 5 feet in HMOS, it's close enough. HCMOS, if it's somewhere within 6 or 7 inches on the same board, it's close enough. So I could wire up my board. It works just fine. But at a nanosecond, you need the capacitors to be within a 1/2 an inch. The good news is that's easy to do. As we start to go to faster and faster rise times, the capacitors need to start moving closer and closer to the switch. And one of the other questions besides how fast are these things switching is you're going to have to start asking the mean question is how much on-die capacitance is there on this device? Because if you're trying to work on a network processor and they don't have enough on-die capacitance, you can't fix any EMC problems as a result of that. Because I said, the depletion wave of the starving power supply is what causes most of the noise. If they don't know the answer to how much on-die capacitance there is, it means they probably didn't do it on purpose. And if they didn't do it on purpose, there's not enough. You want to find another chip because you can't fix it. It's broken inside. It happens to all semiconductor companies, trust me. So, energy is moved by wave action. The only way to reduce system noise is to improve the delivery of energy. If I can't get an amp through my power connection, because I can only get 1/10 of an amp at a time, I have to increase the number of connections. Or I have to make that connection larger. I have to make the impedance lower so the buckets are bigger, or I have to add more buckets. You can either move the things closer together so the round trip time takes less. You can increase the number of pipes that you run in the field through. So each wave cycle you get not 1, but 10 or 5 or whatever it takes to deliver X number of coulombs per second into this IC. If this part needs 4 amps, you have to find some way to provide the plumbing to deliver 4 coulombs of energy. And it won't magically go away. You have to find a way to do that. Unfortunately, most ICs don't enable that very well. So all you can do is fix the PC board to be as efficient as you can to deliver energy to the side of the IC, and then just pray that it's going to work. Now, if the part's got enough mixed grounds and powers so you have a lot of parallel waves going into the part, then you're fine. And the other thing is you can make the traces wider. What I do with my high current power supplies, like from a PMIC to a PowerPC or a network processor, is I'll do a nice wide trace, because I'm not looking at IR drop anymore, over a plane, and then if I can, I'll put a plane over that. So now I've got 2 paths parallel, so I get 2 waves going. If that's not enough energy, and when looking at coulombs per second, right, I add another trace underneath the ground. So now I've got 3 paths for the energy. If that's not enough, I add another one to get 4. And the idea is I put enough pipes in to move the energy. If I don't do it, I'm going to see things called the IR drop that they talk about. And it's really how much of the energy moving through this space is being sacrificed as waste heat as I'm vibrating the molecules in the conductor rather than delivering it to the load. So power, it's all about how far away things are and how long it takes. The first energy comes from on die. As you move farther away from the transistors on the die, it takes longer and longer and longer to get there and come back. So this gives you a relative list of how long it takes to get energy from different places on the board, which gives you an idea of what frequency of switching event you can support based on the distance away from the switch. Basic rule is a 20th wavelength. So if it's within a 20th wavelength, you're probably going to get enough reflections to prevent any noise from the system. Anytime you have to put capacitors outside of that wavelength, the 20th, then you're going to run the risk that either you can't get enough reflections in time, or the size of the buckets is not going to be large enough to deliver this finite amount of energy. I mean, all this stuff has values, it has meaning. Coulombs, while not physical, it's a conceivable concept of how much energy has to be moved. So, getting ready to wrap up. Fields travel in the space between the conductors. It's all about the space. You're designing spaces. You're capturing field. The switching speed of the transistors, not the clock rate, determines behavior of the field. That wavefront moving into the new space. All EMC happens at the wavefront. And if you don't properly manage the wavefront, you're going to have problems with either signal integrity in the case of reflections if you have an imbalanced transmission line, or you're going to have problems with radiated emissions. Signal and power conductions need to be one dielectric separated from ground. Now, on a low layer count board, you don't always have the luxury of a ground plane. Coplanar ground works just fine if you don't have a ground plane. In a 4-layer board, if layer 2 is ground, 1 and 3 are by definition good transmission lines because they follow the one dielectric rule. Layer 4 is not next to layer 2, not in anybody's book. You have to design layer 2 as if it was a single layer board, and every signal has to be adjacent to unbroken ground copper. And if you route from 1 or 3 to 4, you have to use a ground transition via to make a z-axis place for the energy to go so that you can move it around on the board. Otherwise, it has to find a via somewhere. And I guarantee there'll be lots of other signals at the same time looking for that random via, and they won't be happy because they're going to mess with each other. There's no such thing as noisy ground, only poor transmission line design. Ground can't be noisy. Noisy is unwanted changes in field density. Something you didn't put there but happened by chance, right? It's only one conductor. It can't do anything by itself. It takes 2 conductors separated by a space, and what's happening in that space can be noisy. Because somehow I've either got too much happening in traces that are close to it, because you still have that interaction between all conductors. If I've done everything right, I got 2 conductors over a ground plane, and I still have crosstalk, then you use the square of the distance rule. You separate them. If you double the distance, you've reduced the amount of interaction by 4 times. It's 1/4 the interaction. So if that's enough, that's how you work it. All is about understanding the nature of the signals. Dr. Ewing says, thou shalt not split ground. It is almost impossible to manage discrete domains. It costs a lot of money and rarely works. So ignore the data sheets, ignore the app notes, fight with your engineers. I fight with RIC designers all the time. Anytime you break the one dielectric rule, it's going to cause some degradation in the signal that you're trying to move. Now, is that always bad? No. We've gotten away with it for years. Sometimes it doesn't matter. It depends on the behavior of the energy that you're moving in that space. How fast was the switch driving it? Can I let these 2 signals live in the same space and still get the value at the receiver that I need for my system to function without causing an EMC event? Those are the kind of considerations that have to happen. But they have to be a conscious act of design, not a random act of routing. Because Murphy says the one that you don't pay attention to is going to be the one that makes you fail. I have a board that I'm working on now for a Chrysler engine controller for one of my customers. Their board failed a functional test where they were doing some stress testing. They missed 1 ground transition via on a SPI clock line. On an otherwise extraordinarily well-designed 6-layer board with 2 ground planes. 1 ground transition via, and it failed the board. You say, Murphy says the one you miss is the one that's going to cost. So they're going to have to respin and requalify the boards. It's $50,000, $60,000, $70,000, and their customer, the end customer, Chrysler, is pissed off at everybody. So that's the idea. I want to thank my mentors, Rick Hartley, who couldn't be here, and you stuck with me. Ralph Morrison, who is the oldest living EMC engineer. He just released a new book to Wiley called Right the First Time. He got his degree at Stanford in 1947. He's 92. He'll be 93 in January. He still has a valid California driver's license. He plays lead violin in a string quartet, and he's still writing books. And right now he's studying quantum mechanics because he thinks that's the missing key to all this stuff. Really, I spend all the time I can with him. Dr. Todd Ewing, he was past president of the IEEE EMC Society. He was one of the principal researchers at UMR and helped to define what structures do when you build a 3-dimensional structure, what's its behavior in the electromagnetic world, and then he went to Clemson as the endowed chair of the Michelin Automotive Technology Center. Ralph likes to say this. He says, buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. This is what you have to remember. It's very simple. Fields are in space. You design the spaces. Thank you very much for your attention. I hope this has been useful.